Hey everybody, here we go again. Lecture 22, second week of this online activity. Hope you're doing okay. Hope you're taking time for yourself, but spending enough time here to make good progress. Reading quiz for lecture 22, talking about mutual inductance now. Getting into the third of the three components of modern electronics: resistors, capacitors, and now inductors. Here's a new quantity. The mutual inductance of a pair of coils. Two coils separated in space, maybe coupled together with an iron core, maybe not. We generate a changing current in this coil that makes a changing B field in here that makes an EMF. So we want to know how much voltage appears here for a given current over here, what properties. That mutual inductance, you know from your reading, depends, yes, on the shape of the coils, yes, on the number of turns, the relative position of the coils, and maybe this, yeah, some other factors. Your book doesn't talk about that much, and we don't talk about it much, but there's some magnetic effects if we have an iron core that couples the flux. The SI unit for mutual inductance is the Henry. So this answer there is a Henry. Henry is a guy's name. Henry, that's not his first name, that's his last name. His first name was Joe. Joseph Henry is an American physicist. So, inductance in LC circuits. We talk about, I forgot a piece of paper. Sorry, I forgot to grab some spare paper. I told you I was going to do these without editing and cutting, so I had to grab that. We talked about the three components of modern electronics: a resistor, a capacitor, and now this symbol for an inductor. This is an R, this is a C, this is an L. This thing, the capacitor, stores energy in the electric field. Okay, inductor is going to store energy in the magnetic field. This thing dissipates energy as heat. So here's this third component now. I just told you that. Inductor, here's the symbol for inductor, sometimes that, and it stores energy in the B field, as I said. But let's give you an overview before we get into the guts of this thing. I want to compare chapters 24 through 28 to the previous chapter in this chapter we're in now. In chapters 24 through 28, we had a DC system of electric field, and it was constant in time, electrostatics. Electric field makes a steady current, which makes a constant B field. The current was J times the current density, the J was N times EV drift. And there was a current, okay, which had a little bit of d by dt in it, due to that motion, okay. But I itself was constant. There was no time variation of the current. Okay. In chapter 29, we started to relax that constancy. We said that we could have a B field changing in time. And as soon as we allow a B field changing in time, from Faraday's law, we could get an electrostatic, an EMF generated by that in an ideal transformer. Now we're going to let everything vary in time. D by dt of everything is possible. And here's the overall notion of a mutual inductance. A mutual inductor is kind of like a non-ideal transformer. In an ideal transformer, all the flux generated in the primary transfers to the secondary, and we get the transformer relations. Now we're going to have a current in a primary coil, a first coil, a one coil, coil one, and that's going to make some flux, but maybe not all the flux goes through this coil over here. This is coil number 2. It's a non-ideal transformer, and the mutual inductance of that non-ideal transformer is what we're studying today. All the effects we have from here to here actually occur in that coil by itself, okay? And that leads to the notion of a self-inductance of a single coil, and that's this L of self-inductance of an inductor that I talked about here. Okay, so here's the picture, and I'm going to kind of go through this a little faster than I might otherwise. You've got the notes, you've got pause and play on your video. here's a situation. I've got a coil 1 with N1 turns, a coil 2 with N2 turns, that's shown here, N2 loops, okay? And I drive that current I1 here, and I generate an EMF called EMF2, okay, induced by that current dIdt, okay? Faraday's law, you know what Faraday's law says over here. It says that EMF2 is Lenz's law minus N2, the number of turns in 2, times the time rate of the change of the flux in this coil. What's that flux? That flux there is integral B dot dA. Whoops, there's a missing vector stroke. Shame on you, Conrad. That's the magnetic flux through coil 2. So we're going to call that flux phi sub 2,1. And I didn't write this on your notes that you have, but so you may want to write that here. Phi sub 2,1, the order of the subscripts matter here. Phi sub 2,1 is the flux in coil 2 due to the current, time rate of change of current, due to the current in 1. So flux over here due to current in that one. So we'll write that as minus N2 d phi 2,1 dt. Now we're going to define the mutual inductance as this kind of odd collection of units. We're going to define M sub 2,1, the mutual inductance of 2 relative to 1, as the number of turns in 1, the flux to 1, the flux in 2 due to 1, divided by the current in 1. Okay, so this is a real mixed thing. This is the transfer, number of turns in 2, the current in 1, and this kind of thing, which is a hybrid, 2 due to 1. Now, why do we define it that way? We know that the current that phi sub 2,1 is some constant times the current in 1, just because it's a coil that generates a magnetic field. That makes M2,1 a constant, okay? Because that's a constant. That's a constant. So from the definition of that M2,1, phi 2,1 is M2,1 times I1 over N2. So if we take that, then phi sub d by dt of phi sub 2,1 is that quantity there. Oh, that's 1 over N2. Sorry, kind of messy there. And EMF2 is that, okay? That makes this N2 cancel that N2, and we get this kind of simple relationship that says the EMF2 is minus M2,1 times dI1 dt. Now do this all over again. Except from going with the current here and measuring an EMF here, turn this around, turn this around this way, go that way, or flip this within your mind, okay, and do it for the other direction. And whoops, that says that if we do that, E1 due to the current in 2, then everything gets the same except 1 gets replaced by 2 and 2 gets replaced by 1. Epsilon EMF2, EMF1, current dI1 dt, current dI2 dt, and M mutual inductance M2,1 and M12. Now here's the proof by intimidation, you know about proof different ways. Proof by induction, proof by intimidation is the other way. I'm going to tell you this. You have to believe me that if you do the calculation M12 and M21, there's a reciprocity. There's a symmetry there, okay? So that means I can drop the subscripts M12 and M21. There's only one M, okay? And we get these very simple relationships then. These are circuit equation kind of relationships that say that EMF1 is minus M current rate of change in 2, E2 is minus M current rate of change in 1. The unit of mutual inductance is the Henry, If you look for M by itself, it's 1 volt second per ampere. Okay, well, how do you calculate that quantity for a given pair? Here's an example in your book. I don't have the number in front of me. It's the mutual inductance of a Tickler coil round around a solenoid. Okay, a small number of turns here in this secondary, if you wish, due to a solenoid as the primary. So look, the details, more of the details are in your book, but let me just summarize it here. M21 is that, N2 times that over that. Remember, so all we have to do is know the flux here of a solenoid, but we did that before, okay? So that's this result from previous chapters. Do all that, and you get this simple relationship, all known quantities. It's the permeability, the magnetic constant, number of turns N1, number of turns N2, the area divided by the length. Depends on the geometry and other coils. Okay, now that leads to the notion of something that perhaps has more widespread electronic circuit consequences, and that's the notion of self-inductance. Okay, never mind the second coil. There is an EMF induced in the primary coil due to the flux it makes itself. Okay, so all that means is you do the same thing instead of two coils, you do it for itself, and that makes the mutual inductance become a self-inductance, and I get this very valuable circuit element equation. Here's an example in your book, and I telegraph something. This is a simple idea, and kind of you need to know this. I told you way back at the beginning that Faraday's law says that Faraday's law that gives you that EMF induced as a time rate of change of current, of magnetic flux. One way to interpret Faraday's law is that Faraday's law says I have a situation where I've got a change in flux through a circuit, through a loop. No, I don't want that, okay? So, for example, for the self-inductance of an inductor, suppose I have a current going through a mutual inductor, a coil or wire. If the current is constant, then the only voltage I get between here is the resistance, if there is any, okay? But if there's a time rate of change of current, then I get a voltage, okay? What's the polarity? How big is it? It's this big. What's the polarity? Okay, but it depends on two things. It depends on the direction of the current and whether the current is increasing in time, I should have said there, increasing in time or decreasing in time. Suppose the current is going this way, so that's that direction in both cases, current going left to right. In this case, it's getting bigger with time, okay? In this case, it's getting smaller in time. The induced EMF polarity opposes the change in the magnetic flux, okay? Well, how do I do that, okay? Here's a current flowing through here. If the current wants to increase, that's going to make more B field. That's going to make more flux through here. Faraday's law says, nope, I don't want the flux to increase. So I'm going to induce a voltage that goes that way that makes the current not want to go that way, huh? Think of how I would do this. I would take a battery here, positive and negative, positive and negative here, connected here, okay? Conventional current from the battery goes that way, okay? But if I want the inductor to oppose that current, I want that current from the inductor to flow that way, opposing it. That gets that way. So that's that example. Here's the same example, current going left to right, but now I is decreasing in magnitude as a function of time. That would make the flux through here decrease. That would say, tell Faraday, I'm going to let the flux here decrease. And Michael Faraday says, not going to have it. I want the flux to be constant as much as I can, so it'll go that way. That'll bump up the current going that way. Here's an example for the solenoid. You can work through that. Example 30.3 here, and you get a result there. Okay, that's 14 minutes. That's kind of a target. Maybe I went too fast. We'll see. You guys take care. Be safe. Spend time with your family. Practice social distancing. Things are getting bad out there. They're going to get worse. I hope you're doing okay. Hope you're doing safe. Bye-bye. See you next time.